So when we're talking about finding the area bounded by a polar equation, we're always going to be talking about finding the area between two angle lines versus two x coordinates or y coordinates. So these angle lines, which you see here as beta and alpha, right? These lines always come out of the pole, which is the origin, right? So when we're finding the area of a piece of a polar curve, it's very similar to finding the sector of a circle, right, which is just a fraction of a circle. So this formula, when we have it in the angle in radians, turns into 1/2 times theta times r squared. So we can convert this into area of a polar curve by just creating that as an integral, where we integrate that formula between the two angle lines that we're trying to find. So just some things to remember: your R equation is always the distance from the pole to the curve, and you're never going to really have to change that. They're always going to give you that equation. You're not going to have to figure it out. And then your alpha and beta lines are just where the curve is bounded in between. So sometimes you have to solve for those to figure out what's your starting and stopping point. So the hard part about this is first, finding those boundary lines, the angle lines that you need to integrate between, and then sometimes there's a little bit of trig manipulation in these because polar curves are so often based on sine and cosine. So we're going to pull in some trig identities today. So the first example I want to look at is I want to find the area bounded by the cardioid. Thank you, autocorrect, for not making that the right word, of r equaling 1 minus sine of theta. So we have this very easy curve here, right? It's a very rounded heart. We're going to find the area that's inside of it. So because this function is based on sine, and we know the period of sine is 2 pi, we're going to actually find the area between 0 and 2 pi. Because if we plug in 0, we're going to actually start here because we're going to get the point 1. So remember it's r comma theta. And then if we plug in 2 pi, we come back to that same spot. And every number in between would be the rest of the curve. So our area here is going to be 1/2 times the integral of 1 minus sine theta squared, d theta. Okay. Right, so if we go ahead and square this out, we're going to get 1/2 times the integral from 0 to 2 pi of 1 minus 2 sine of theta plus sine squared of theta d theta. So now this part we know how to integrate really easily, but the second part, the sine squared, is not quite so simple to do, right? It's not an integral that you know right off the top of your head. It's not it's not like an integral formula you know. So we're gonna have to do a little bit of manipulation. So let's go ahead and integrate the first part. So that's gonna be, if I integrate 1 minus 2 sine of theta, that's gonna give me theta plus 2 cosine of theta. Right, so that's just that integral there. And we're evaluating that from 0 to 2 pi. And then I'm going to have 1/2 times the integral from 0 to 2 pi of sine squared, since I have not integrated that yet. Okay, so sine squared, we need to reduce that power so that way it's something that we can easily integrate. So an easy way to do that is, I'm going to go over here for some space, is the cosine of 2 theta formula. So the double angle formula for cosine has 3 different iterations, and the one that we want to use here is that cosine of 2 theta is also equal to 1 minus 2 sine squared of theta. So this helps us to create what's called a power reducing formula. So I've got the equal sign in there. If I rearrange this, I'm going to move the 2 sine squared over, so it's positive 1 minus cosine of 2 theta over here, and divide by 2, I get that sine squared of theta is also equal to 1/2 of 1 minus cosine of 2 theta. So we're going to substitute that expression in for sine squared because cosine of 2 theta is easier to integrate. We can actually integrate it. And there we go over here. Okay, so if I evaluate this part, I get 1/2. If I plug in 2 pi, I get 2 pi plus cosine of 2 pi is 1, so that's 2. Minus 0 plus 2 times cosine of 0 is also 2. So those 2's are going to cancel out, which is super nice. And we're just going to get 1/2 of 2 pi there, so we'll get pi. So now worrying about this, I'm going to get 1/2 times the integral from 0 to 2 pi. And replacing sine squared with that formula we just wrote down, 1 minus cosine of 2 theta, all times 1/2. And then d theta. So I'm going to actually multiply the 2 halves together and then split that into 2 different integrals again. So the first part, we get 1/2 of 2 pi, so that's pi. And then I'm going to get 1/4 the integral from 0 to 2 pi of 1 d theta minus 1/4 the integral from 0 to 2 pi of cosine of 2 theta, just splitting it up using my integral properties. So the integral of d theta is really easy. That's just going to be 1/4 of theta evaluated from 0 to 2 pi, and we'll bring the pi down from our previous part of the answer. Now the second one over here, I have to do a u substitution. So if I let u equal 2 theta, and I take the derivative, du is then equal to 2 times d theta, which means that 1/2 du is equal to d theta. So if I substitute that in, I'm going to bring another 1/2 out there. So now I'm going to get minus 1/8 times the integral. And if I replace my limits of integration, if I plug in 0 to u, 2 times 0 is still 0. And then 2 times 2 pi is 4 pi. And then this becomes cosine of u. And then we get du. Okay, so going back over here, if I plug in 2 pi here, right, because the 0 is going to cancel out, a quarter of 2 pi is pi over 2. So I get pi plus pi over 2 here, minus 1/8 times the sine of u. And that's going to be evaluated from 0 to 4 pi. So if I evaluate that, sine of 4 pi is 0, and sine of 0 is 0, right? So that part doesn't even matter. So we get pi plus pi over 2, so the area inside of that cardioid is 3 pi over 2. Right, so these often become a lot of work, especially if you're not using a calculator, right? If you're using a calculator, you just set up the integral, plug it into your calculator, and get the decimal approximation, not a big deal. So just something to be careful of with all of the trig substitution. We're going to do one more here, and we're going to find the area of one petal of r equaling 4 cosine of 2 theta. So we need to find our boundary lines for this. So I'm going to just start plugging in some easy numbers to evaluate for my r values. So I'm going to plug in theta values and get out r values. Okay, so if I plug in 0, right, 2 times 0 is 0, cosine of 0 is 1, so I get 4. So at 0, I'm at 4, so I'm at this point right here. Okay, another easy one to plug in would be pi over 4, right, because 2 times pi over 4 gives me pi over 2. Cosine of pi over 2 is 0. So this is my pi over 4 line here, so that brings me in right here. So my curve is moving in that direction. So I have half of a petal there. And then if I move back out, say I plug in pi over 2, right? That gives me pi. That's going to give me -4. So at pi over 2, I'm down at -4. So we're going this direction. So there's a couple of different ways to do this. So when I traveled from 0 through pi over 2, right, I'm in these parts. The great thing about polar curves, especially the rose curves, is that they're symmetric. So we actually have, right, a full petal here. Right. And if you just read over the Post-it notes, I actually use different angle lines. It does not matter, right, because you're going to get the same angles. So why don't we integrate between 0 and pi over 2? So for my area, I'm going to get that this is 1/2 the integral from 0 to pi over 2. And then we have 4 cosine of 2 theta squared, d theta. Okay, so 4 squared is 16, half of 16 is 8, so I have an 8 on the outside. And then I have cosine squared of 2 theta. So now just like the last one, we need to get rid of the squared power. So we're going to use a different double angle formula. So I'm going to write the double angle formula a little differently. Instead of thetas, I'm going to use u's. So cosine of 2 times u, whatever your angle is. Another iteration of that is that it is 2 cosine of theta. 2 cosine squared of u, whatever your angle is, minus 1, right? So if I solve for cosine squared, I'm going to bring the 1 over, and then I'm going to divide it by 2, so bring over a half. So now this one's a little tricky because we started with a double angle on the inside. So what we're going to do here, right, our u in this case is already 2 theta. So here, this is going to become 2 times 2 theta, the angle I already had inside. So I'm going to actually get 4 theta inside of my integral. So we're going to go ahead and substitute this in. So I get 8, and then remember, I'm going to have times 1/2 out here. From 0 to pi over 2 of cosine of 4 theta, right, plus 1. D theta. Just zooming out. Let's make sure we check that work. Yep. Right, so it's just double the angle that you started with. Okay, so that gives me a 4 on the outside. And then I'm going to go ahead and break this into 2 integrals. So we have cosine of 4 theta d theta plus 4 times the integral from 0 to pi over 2 of just d theta. Right, so that part's really easy. It's going to be 4 times theta from 0 to pi over 2. And then over here, we're going to need to do a u substitution. Right, so again, I'll let my u be the inside angle, so 4 theta, which means that du is equal to 4 d theta. Now, hey, look, I have 4 d theta, right? 4 d theta is right here. So all of that's going to be replaced with du. So if I replace my limits of integration, if I plug in 0, I'm still going to get 0. 4 times pi over 2 is 2 pi. And this is going to become cosine of u du. Okay, so that's going to equal sine of u from 0 to 2 pi plus 4 times pi over 2 minus 0, and then that is going to give me 2 pi on the end, and sine of 2 pi and 0 are both 0, so this is 0. So the angle of the area of one petal is just 2 pi, which means that the area of the full rose curve, right, if we multiply that by 4, would be 8 pi.